Okay, so now what we are going to look at is the congestion control problem. So the flow control problem is how to adjust the sending rate according to the resources available at the destination. Now the congestion control problem is how to adjust the sending rate according to the resources available in the intermediate networks. So think about it. So the routers in the intermediate networks have a queue size. So if the router's queue gets full, it's not going to forward any additional packets. Similarly, each network has its own bandwidth limitations. So you cannot send beyond a certain rate at the intermediate networks. So even if the receiver has a lot of buffer space to accept any incoming data from the source, the intermediate networks may not be able to transfer data at the same rate. So we have to consider both flow control as well as the congestion control problem. So it's not sufficient for the destination to be able to accept whatever data that comes based on its buffer space. If the intermediate networks cannot send anything, data won't make it to the destination first of all. Alright, so that is why congestion control is also an important thing to be considered, and we have to decide the effective window size, which is additional bytes that the source can send based on both what is called the advertised window, which is what we just saw for flow control, as well as what is called the congestion window, which is going to be estimated based on the congestion control mechanism we are going to see, and then decide how much more we can send. Okay, so far we did advertised window minus the outstanding bytes. So that is the last byte sent minus last byte acknowledged. Now we have to take the minimum of what is called the congestion window and the advertised window minus the outstanding bytes that have been sent and not yet acknowledged as the effective window size the source can send furthermore. Now the advertised window is something the destination can notify the source using the acknowledgement packet, but it's not that easy to know what is the congestion window in the internet, because we cannot expect the routers to advertise that amount of queue buffer space or queue size available at the routers to every source out there. That's not possible. So we have to use a trial and error mechanism at the source side to estimate the congestion window. And one approach that is typically used is to measure the round trip time it takes at the source side. Since it has sent the data packet, how much time it takes for the acknowledgement to come back. So the round trip time is a measure of how much what are the resources available at the intermediate networks, at what rate the intermediate networks and the routers can transfer the data. Now if you don't get the acknowledgement, you time out. So a timeout is typically to be considered a measure of congestion, because a timeout happens if the data packet is kind of not making it to the destination, and the destination is not going to send an acknowledgement if it does not get the data packet. Now assuming that the other reasons why a timeout could happen, like just typically a packet loss due to some non-bandwidth issue due to the routers not dropping the packet for some other reason, that's not reasonable to expect, because packet loss happens because routers are dropping the packet, and routers are dropping the packet because the queue size is full. The other reasons why routers could drop the packet is if the packet could get corrupted on the way, or if the time to leave the TTL field reaches 0, and so on, things that we saw the earlier modules. They are possible, but they are not the main reasons for a packet to get dropped at the routers. So if a timeout happens at the source side because of not getting an acknowledgement, that's typically to be considered as a packet loss or packet dropped at the router. So and the drop happens due to the router's queue getting full. So when a packet drop happens, that means the source should of course retransmit the data packet, but the source should not retransmit at the same rate. It should slow down, because already it was sending at a certain rate and packet drops start occurring. So you should not keep bombarding the internet with the same sending rate. So that will actually escalate the congestion in the internet. So you should slow down. Now, one way to slow down is to what you call extend your timeout period. So we are going to see an algorithm where the source would time out say for 200 seconds, which is based on the round trip time. Now, if a timeout happens and you don't get the acknowledgement, you don't still wait for another 200 seconds to send another data packet. You wait for a longer time to get the acknowledgement, because there's congestion going on in the internet, so the routers will take some more time to forward the data packets. So that means you have to wait for a longer time to time out and retransmit a packet for which you don't get the acknowledgement. So that is a standard way in which the source will slow down its sending rate, and also how much it is sending, so per window size. So that's what we're going to see in all the details as we proceed. So the first thing we'll look at is the timeout mechanism. Now, one thing to think about is how to measure the round trip time, and for what kind of packets we could really measure the round trip time. So let us just look at a scenario like this. The sender has sent a packet. It's like you can treat it as original transmission, and the receiver got it. But let us say the acknowledgement is lost somewhere, or it takes time for the acknowledgement to come, or for some reason the acknowledgement for the first original transmission didn't make it to the destination, to the source. So the source will time out and retransmit. Now the destination sends an acknowledgement, and the acknowledgement now makes it to the source. Now the source has sent the same data twice. It was sent originally here and it was retransmitted because the source timed out and did not get the acknowledgement. Now, with reference to which transmission, the source has to measure the round trip time. Does it has to measure the round trip time based on the first original transmission or based on the retransmission? So the round trip time is the difference between the time at which acknowledgement was received and the time the packet was transmitted. So what was the transmission time? Should it consider the first retransmission time or the original retransmission time? If the source considers the original transmission time as the time for which the transmission needs to be considered, and takes the difference between the time acknowledgement came and the time it was originally transmitted, it's not an accurate measure of the round trip time, as we can see in this case. Because from the source point of view, it doesn't know whether this acknowledgement is meant for the original transmission or the retransmission. We are looking from a centralized point of view, so we know what is going on both sender and receiver side. But in the real world, from the sender's point of view, when it gets an acknowledgement, it doesn't know whether the acknowledgement is meant for this retransmission or the original transmission. So if the sender thinks this acknowledgement is for the original transmission, then from what we see at both sides, it's not an accurate way of estimating the round trip time, because its acknowledgement was actually sent by the destination for the retransmitted data packet. Now what if it's the other way? If the sender thinks the acknowledgement coming is really for the retransmitted packet, but if the acknowledgement was really sent for the original transmission, then the sender will again be wrongly estimating the round trip time. So in the first case, it will be overestimating the round trip time, because the actual round trip time is the time at which acknowledgement received minus the time it was retransmitted. So you are actually overestimating the round trip time. In this case, you are underestimating the round trip time, because the actual round trip time is the time at which acknowledgement received minus the time of original transmission. So in both cases, you are wrongly estimating the round trip time from the sender's point of view. So one way to fix this problem is, when you want to measure the round trip time between the sender and receiver, you measure the round trip time only for those data packets that were sent only once and not yet retransmitted. So you wait for the acknowledgements for those data packets to come and take the time difference between the time at which the acknowledgement came and the time the packets were originally transmitted. So that is the solution to fix this problem of underestimating or overestimating the round trip time. Okay, so just measure them for the packets that were just sent once and not yet retransmitted. That's the solution. Now, so what we are going to look at is an algorithm to estimate the round trip time, and based on that we will set the timeout. So this is a simple algorithm where the estimated round trip time, again all these things are maintained at the sender side, is a weighted average of the sample round trip time. So I showed you the way the sample round trip time can be measured. So you send a data packet and wait for the acknowledgement for the particular data packet to come, and you measure the time difference. So that is the sample round trip time. So as you keep sending data packets, you will start getting several samples of round trip time. Now you should not just take the current round trip time that you estimated for the latest sample as the estimated round trip time for the internet for the between the sender and receiver, because it's just a sample that you are measuring. So that's why you have to take a weighted average. You should not just consider the current sample round trip time as the measure of the round trip time between the sender and receiver. So when you take a weighted average, that means you have to give the sample round trip time for the latest sample some weight, as well as keep a kind of average estimated round trip time measured based on history so far, and give that some weight. So let us say the weight parameter is alpha. So it's in the range of 0 to 1. So if it's alpha is say 0.7, then you give 70% importance to history based on what you have seen so far, and 1 minus alpha, so 1 minus say 0.7, 0.3, so 30% weight to what you see for the current sample. And after you do the math, whatever you come with is considered as the latest estimate of the round trip time, the average estimated round trip time, and use that for the next sample and keep going during the process. So when you don't get an acknowledgement, then you time out. So how long you have to wait to time out? So the timeout for the current window of packets that you have sent is 2 times the latest value of the estimated round trip time. So that this is the timeout, or this is algorithm to estimate the round trip time and also adjust the timeout accordingly. So let us take an example to go through this math so that it's clear to you how this is computed and adjusted. So I could give you these as the round trip times, the sample round trip times at the sender side, say 150 milliseconds, 300 milliseconds, 250 milliseconds. So these are for the different data packets, sample round trip times, and then there's a timeout happens. Then for the next packet there's 400 milliseconds, another timeout happens, and then 700 milliseconds. So based on this sequence of sample round trip time values, we should now be able to compute at the sender side what is estimated round trip time after each sample round trip time is measured, and what's the timeout accordingly. So to begin with, the first sample RTT is 150 milliseconds. So the estimated round trip time for the first sample is also set as a sample RTT, which is 150 milliseconds. The timeout is all the time 2 times the estimated round trip time, which is 2 times 150, so that is 300 milliseconds. Now the next sample round trip time is 300 milliseconds. So I need to give you also the alpha value. So let us assume here alpha is 0.5. So you may give 50% importance to the history and 50% importance to the sample round trip time. So it is 0.5 times the sample round trip time, which is 300, plus 0.5 times the estimated round trip time so far, which is 150 milliseconds. So if you take the if you do the maths, the new estimated round trip time is 225 milliseconds, and the timeout is twice the new estimated round trip time. So 2 times 225 is 450 milliseconds. Now the next sample RTT is 250 milliseconds. So based on this, the new estimated round trip time again is 0.5 times 250, the sample RTT, plus 1 minus alpha, so 0.5 times the estimated round trip time. So that is currently 225 milliseconds. So if you do the math, it comes out to be 237.5 milliseconds. That's a new estimated round trip time, and the timeout is twice this estimated round trip time, so that is 475 milliseconds. So the sender would have waited for this latest timeout value, which is 475 milliseconds, but it has not got an acknowledgement based on which it could have measured the sample round trip time. So the sender times out. So based on this timeout, we have to now adjust the estimated round trip time. So as I said, if you time out, we have to extend how long you will wait for the next acknowledgement packet to come. You don't want to wait for the same 475 milliseconds and retransmit the packet because you timed out because probably there's congestion happening in the internet. So you want to wait for a longer time before you retransmit another data packet. So 475 milliseconds. So when you time out, the way you extend the round trip time, estimated round trip time, is 2 times the current estimated round trip time. So the current estimated round trip time is 237.5 milliseconds. So you make it 2 times that value. So that is 475 milliseconds. That is your new estimated round trip time. And the timeout is accordingly again 2 times the new current estimated round trip time. So that is 2 times 475. That is 950 milliseconds. So basically, you can see everything doubles. So for the next data packet or window, the source will wait for 950 milliseconds to wait for an acknowledgement and before retransmitting the data. So it gets acknowledgement within 400 milliseconds. That's the next sample RTT. So the new estimated round trip time is going to be 0.5 times the sample RTT plus 0.5 times the current estimated round trip time. So the math will come out to be 437.5 milliseconds. That's the new estimated round trip time. And the new timeout is going to be twice of this, which is 875 milliseconds. So you can see, even though it has been estimated 950 milliseconds as timeout, the source gets the acknowledgement within 400 milliseconds. So for the next window, the timeout has actually reduced a bit. Now it's better to be kind of little conservative rather than being very optimistic and having a lower timeout. So it's okay to have a larger timeout. Eventually you will be able to figure out how much time to wait according to the congestion level in the internet. Now let us say a timeout has again happened, so you have to estimate double the estimated round trip time from what it is currently. So 437.5 times 2. So 875 milliseconds, and the new timeout is again twice the current estimated round trip time. So 2 times 875 is 1750 milliseconds. And the next sample RTT is measured to be 700 milliseconds. So accordingly, your new estimated round trip time is 0.5 times the sample RTT plus 0.5 times the current estimated round trip time. So you can see you will kind of be able to find a reduced estimated round trip time based on sample RTT. So it comes out to be 787.5 and double this, that's the time of 1575 milliseconds. So this is how the sender will keep adjusting its timeout value and the estimated round trip time based on the sample RTTs it is measuring for the data packets or window of data packets that are sent. Okay, any questions? So let me stop for a minute and save this video.